What specific problem does the Img-Diff dataset aim to solve within the context of multimodal large language models, MLLMs?
The Img-Diff dataset specifically aims to enhance the fine-grained image recognition capabilities of multimodal large language models, MLLMs, by challenging them to analyze pairs of very similar images with subtle object alterations. This dataset addresses the limitations of existing visual instruction tuning datasets, which often focus on single images, by requiring MLLMs to articulate differences within designated regions of paired images. By integrating Img-Diff into the training process, the dataset empowers MLLMs to better scrutinize intricate areas within images, thereby improving their performance in visual question answering (VQA) tasks and other downstream applications. The evaluation results demonstrate that fine-tuning MLLMs like LLAVA1, 5 and MGM with Img-Diff leads to significant performance improvements on image difference benchmarks, indicating its effectiveness in augmenting MLLM's capabilities in discerning subtle differences and enhancing overall visual understanding.
How does the proposed method of generating the Img-Diff dataset work? Illustrate the process step by step, including key components such as the difference area generator and the difference captions generator.
The proposed method for generating the Img-Diff dataset involves several key steps and components. First, similar image pairs are created through object replacement using a generative model, specifically Stable Diffusion XL, which generates images based on modified captions from MS COCO. Next, the difference area generator identifies the locations of object differences between the image pairs. This involves three main processes: applying the image similarity filter to ensure high similarity between images, using FastSAM for image segmentation to crop images based on bounding boxes, and employing the difference detector to confirm significant differences between cropped sub-images while filtering out overlapping bounding boxes. Following this, the difference captions generator creates descriptive captions for the identified differences. In the first stage, it labels the bounding boxes by selecting regions with the lowest similarity and generating content captions using the MLLM LLAVA next. These captions are then filtered for accuracy using the image text matching filter and the captions similarity filter. In the second stage, the generator highlights the differences in the images and produces final difference captions based on the content captions and the highlighted regions. This structured approach ensures the dataset's quality and diversity, ultimately enhancing MLLM's capabilities in recognizing and describing subtle image differences.
Can you provide a specific example illustrating how the Img-Diff dataset enhances MLLM's ability to recognize subtle differences in images? Walk through the main algorithm steps using this example.
The Img-Diff dataset enhances MLLM's ability to recognize subtle differences in images through a systematic process of generating and analyzing image pairs. For instance, consider the generation of a pair of similar images where an object, such as a red car, is replaced with a blue car. The main algorithm steps begin with the image pairs generation, where the original image caption is modified to reflect the object change, and the advanced Stable Diffusion XL model is used to create the new image. Next, the difference area generator identifies the bounding box around the replaced object using segmentation and similarity filters, ensuring that the images are highly similar but not identical. Following this, the difference captions generator produces specific captions for the bounding box, highlighting the change from the red car to the blue car, which allows the MLLM to focus on the precise area of difference. Finally, the fine-tuning of MLLMs like LLAVA1, 5 to 7b with this dataset leads to improved performance on benchmarks such as MMVP, demonstrating their enhanced capability to detect and articulate subtle differences in images.
What empirical benefits were observed after incorporating the Img-Diff dataset for fine-tuning LLAVA 1.5 to 7b and MGM-7b? How do these improvements compare to state-of-the-art models like GPT-4v and Gemini?
after incorporating the Img-Diff dataset for fine-tuning, both LLAVA1, 5-7b and MGM-7b exhibited significant performance enhancements across various benchmarks. Specifically, LLAVA1, 5-7b surpassed the performance of LLAVA1, 5-13b, and achieved notable improvements on the MMVP benchmark, even exceeding state-of-the-art models like GPT-4v and Gemini. The fine-tuned MGM-7b also demonstrated substantial gains, particularly on the Spot the Diff benchmark, indicating enhanced capabilities in detecting subtle differences between similar images. Overall, the fine-tuning with Img-Diff resulted in an average score improvement of 3.06% for LLAVA 1.5-7b and 1.28% for MGM-7b across multiple MLLM benchmarks, showcasing the dataset's effectiveness in bolstering MLLMs' visual question answering and image analysis skills. These results underscore the dataset's role in elevating the performance of MLLMs to align with or surpass existing state-of-the-art models.
Explain the validation process used to test the effectiveness of the Img-Diff dataset. What benchmarks and evaluation metrics were employed, and why are they appropriate for this task?
To validate the effectiveness of the Img-Diff dataset, we fine-tuned the multimodal large language models, MLLMs, LLAVA1, 5 and MGM using our dataset and evaluated their performance on several benchmarks including MMVP, Spot the Diff and Image Edit Request. These benchmarks are particularly relevant as they focus on assessing the model's capabilities in recognizing subtle differences between similar images, which aligns with the primary objective of the Img-Diff dataset. Evaluation metrics such as Blue, Meteor, CIDR-D, and Rouge-L were employed to quantify the model's performance in generating accurate descriptions of image differences. The choice of these metrics is appropriate as they provide a comprehensive assessment of the quality of generated captions, ensuring that the models not only identify differences but also articulate them effectively. The results indicated significant performance improvements, with LLAVA1, 5-7b and MGM-7b surpassing state-of-the-art models, thereby demonstrating the dataset's utility in enhancing MLLM's image difference recognition capabilities.
What limitations or drawbacks did you identify in the proposed Img-Diff dataset and method? How do these limitations affect its practical applicability in real-world scenarios?
The proposed Img-Diff dataset and method exhibit several limitations that could impact their practical applicability. Firstly, the dataset's reliance on high similarity thresholds for image pairs may inadvertently filter out valuable instances, leading to a potential loss of diversity and richness in the dataset, as indicated by the performance decline when the similarity threshold is lowered. Additionally, while the dataset demonstrates high quality in terms of bounding box differences and caption accuracy, the filtering processes may introduce noise if the similarity is not adequately maintained, which could hinder the model's ability to generalize in real-world applications. Furthermore, the dataset primarily focuses on object replacement, which may not encompass all scenarios encountered in practical image analysis, limiting its versatility. Lastly, the exploration of object removal data, while promising, suggests that the dataset may not fully address the complexities of object presence and absence in diverse contexts, potentially restricting its effectiveness in comprehensive visual question answering tasks.